All right, let's try another take at that. So let me get my screen shared here. There it is. Maybe. Come back. Okay, so today we'll be going over substitution and elimination reactions of alkyl halides. So how do I make this go away? Oh, no, 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 that's not what I wanted to do. Come back. Okay, so here we go. So here we have the mechanisms and rate laws for substitution and elimination reactions. With the substitution reactions that we see on the left-hand side here too, the SN2 and SN1, with those reactions, atoms are being swapped due to a sigma bond being broken and a new sigma bond forming. So the two types that we have are SN2 and SN1. SN2 has the rate law that you see right here, rate law, rate equals, oh, no. All right, so we see that K, Rx, and nucleophile, and we see that it's a concerted mechanism. It follows second order kinetics. So everything's happening in the same step. Now we do have like an intermediate step, but it happens for such a brief moment that that molecule can't be isolated. So we have the leaving group that we see here is the X. It'll be taking those electrons with it, and it'll be leaving at the exact same time that that nucleophile is coming in and doing what's called like a backside attack. So basically it has to attack at 180 degrees at the exact same time that that group is leaving. So we see that intermediate step here. And yeah, again, that's a concerted mechanism, which is why that specific stereochemistry has to be there. Then in SN1 reactions, it's actually going to be a multi-step mechanism. We have the leaving group taking those electrons in the first step in the rate determining step. So better leaving groups, you look at chlorine, great leaving group, but not as good as bromine, not quite as polarizable, not as big, not as willing, not as fast to take those electrons and get out of Dodge. So better leaving group is going to make that step a little bit faster. So it's really kind of just up to the alkyl halide and the concentration as well as the strength of the alkyl or the substitution of that alkyl halide, or not substitute, strength. Oh my goodness. Which yeah, weaker bases, better leaving groups, so on and so forth. So we have that leaving group leave, first step, then second step, we have the carbocation intermediate that forms. Now, if there is something more stable that could be formed in that step, it is going to rearrange itself. We are going to see that carbocation rearrange, which we don't see in this. It's not necessary. And then with the final product here, we'll actually have both stereoisomers. So we'll see a retention and inversion if chiral. And then when we look at elimination reactions, it's a little bit different than the substitution reaction because there's a loss of elements from the starting material to form a new pi bond in the product. So with an E2 reaction, kind of like SN2, it's all happening in one step. We have that leaving group taking those electrons, getting out of there, at the same time that we have the base deprotonating. So it's taking that proton, that hydrogen, and not the electrons though. The electrons are going to stay and they're going to form that new pi bond. So we see like that intermediate step that is so brief that it can't be concentrated or observed. And then we see that formation of the new bond. It's also going to follow Zaitsev's rule, which we will talk about later. But basically, it's going to form the most substituted carbon-to-carbon double bond that it possibly can. So in E1 reactions, same thing as SN1. It's the same rate law. We have more than one step. We have the leaving group taking those electrons, getting out of Dodge, and the rate determining step. And then we have the base taking that hydrogen, that deprotonation step. And those electrons from that hydrogen are going to plop down into that double bond. Now, if the carbocation intermediate can form a more stable carbocation, it will. Again, in this example, it did not need to, so we don't see that happening, and we see the formation of our beautiful little double bond here. So we're going to move on. Did I leave anything? Oh, with both E1 and E2, the more substituted halides will react faster. Same thing with the SN1 reactions, which let's talk about that. So with SN2 and SN1 reactions, here are some specifics that we're going to see. We're going to see that SN2 is special and it actually prefers a less substituted alkyl halide or substrate, preferring methyl the most, followed by primary and secondary, and it doesn't really like to go through with tertiary. There's a little too much steric hindrance. We were talking about that back attack, that 180 degrees that we need. Yeah, that's not as simple with a tertiary substrate, which is also why when we look at the nucleophile, we want a good nucleophile that has a good charge, a negative charge on it. We also want one that is not too sterically hindered. So if that nucleophile is charged, but it's attached to something big and bulky, its wingspan isn't going to be able to fit through, and it's not going to be able to get to that electrophilic site, and that wouldn't be good. It wouldn't like that. So when we're looking at solvents, or well, first let's compare. So with the SN1 reactions, they're actually not going to take place with the methyl. We're not going to see that so much. Same with the primary. We will see it happening with the more substituted substrates like the tertiary and secondary. And when it comes to the nucleophile, it's not as important about the nucleophile. It's good if we're neutral. We can have a charge, we can be neutral, we're good. But let's look at solvents, because with the SN2 reaction, we need a polar aprotic solvent. A protic solvent is actually going to slow the reaction down by stabilizing the nucleophile. It basically is forming a solvent cage around a good nucleophile through hydrogen bombing, or bonding, not bombing, effects, which the nucleophile, it actually has to try to break out of those effects, which it will eventually, but it has to break through those hydrogen bonding effects to be able to find the electrophilic site. So that's going to slow it down. It's not going to like that. We want aprotic solvents. Whereas in the SN1 reactions, we actually want a protic solvent to stabilize that carbocation intermediate. It's actually super useful here. Now, with stereochemistry, back again to that 180 degrees, that back attack, we're going to see an inversion of configuration of chiral. The leaving group and the nucleophile have to be 180 degrees apart for that attack as well. So yeah, we're going to see that inversion. With the SN1, there's not really specific stereochemistry when it comes to the reaction happening. However, with the final product, if that starting material is chiral, we're going to see retention and inversion of the configuration, leading to a racemic mixture. So basically a 50-50 mix of the R and S isomers. And then move on to some elimination specifics. Both of these guys are going to prefer the more substituted substrate. So we're going to see, the more substituted alkyl halide is going to be the best. We want tertiary, awesome, great. Secondaries go cool too. So is first. But with E2, we might see some of the primary. E1, we're not going to really see that. We're definitely not going to see methyl, but we're not going to really see the primary because it leads to a really unstable carbocation, and nobody likes to be unstable, right? Okay. So with the base, with E2 and SN2, one thing you can kind of see is, okay, we have a strong bulky base is good for E2. We're not worried about steric hindrance here, and the stronger the better. So we want strong bases. We're cool with the bulky bases. If you see a really bulky base, it's probably an E2 reaction. Whereas in E1 reactions, a weak base is okay. It actually favors a weak base reaction. With the solvent, E2, it's cool with any solvents. It's going to favor an aprotic solvent because that's going to help speed that reaction up. We're not going to get that solvent cage going on. But with an E1, it does need a protic solvent to stabilize that carbocation intermediate. And then with the stereochemistry, with the E2, with it being all one step, we're going to want the antiparaplanar or transdiaxle stereochemistry to make that attack, to make that possible. Whereas in E1, it doesn't really matter. Now the regiochemistry is important because when it comes to the product, just like how we wanted the most substituted alkyl halide to start with, we're going to want the most substituted carbon to carbon bond. We're going to want the most stable substituted product. So you will see a major and sometimes a minor. Sometimes you'll only have one, but you will sometimes see a minor product. We're looking for the major product. That's what's going to be most stable. That's what's going to be formed in the largest percentage. Things go correctly, I assume so. But all right, so to recap, when it comes to the substrate or the alkyl halide, the more substituted, the better, unless we're looking at SN2. Remember, steric hindrance. So if it's primary, it's probably SN2. And I think that's the one they all, so when it comes, oh, here we go. When it comes to the leaving group, so that alkyl halide that's taken off, it doesn't matter what reaction type we're looking at, the better leaving group is going to equal the faster reaction regardless. That's because if that leaving group really wants to take those electrons and get out of there, that's part of the rate determining step in both of them. Well, it is the rate determining step in the SN1 and E1. But you know, it's a big part of it in E2. So if that leaving group is really apt to leave and get out of there, the reaction is going to proceed faster regardless. And yeah, I feel like I've probably gone over everything I'm going to remember right now without rambling on and making these videos insane for you to watch. So, oh no, what did I do? Okay, here we go. So let's go back to Zoom. Awesome. Sweet. So there you have it. You have SN1, SN2, E2, and E1 reactions. A great night.